Okay, hello everyone. It's really great to have you back with us again for day two. I'm Lori Krings. I will be your moderator again today as we keep exploring water quality in the distribution system. Thank you guys for your participation and your engagement yesterday. Your chat comments and questions really add so much when it's interactive. It really is a lot more fun, I think, for everybody. So please continue to do that if something should strike you. And we'll basically have the same format as we did yesterday, but we are going to just do a quick look at our plan for today and just look at maybe some reminders and just a couple announcements for today. Okay, so essentially, really the only main thing that's changing today is the day that you will, if you need a certificate of attendance, today's the day that you will complete that SurveyMonkey link, which I will send to everybody at the end of today. It will go into the chat window. So you don't have to do anything yet at the very end of today. But that's really the main difference for today. We're still going to record everything. We're still going to actively use polls and ask that you guys put any questions you might have either into the chat or into the Q&A. And I'm going to hold those questions for you just like yesterday and keep a list, and we will have that dedicated Q&A section at the end. We'll also be taking a break. So it's going to feel a lot like yesterday. But if you do have any questions about anything, please do let me know. And we got the same team with us again today. Ingrid Sandberg's here to help us on the technical side of things. Thank you, Ingrid, for coming back. And of course, we know we're in good hands with Daryl Gotham and Greg Pearson as our instructors. So welcome back to both of you, and thank you for being here again. And the floor is yours.
Okay, thank you, Lori. Did you have anything you would like to say, Daryl, before we start?
I'm all set, Greg.
Okay, great. Well, welcome everyone. We're glad you're back today. Today we're going to be covering, beginning with corrosion control, and we'll do a little bit on cross-connection control, talking about backflow. And both of these are focused on from the perspective of improving and protecting distribution system water quality. And then we're going to hand the platform over to Daryl, and he'll be talking about sanitary surveys and sampling and monitoring. And that will round out our day today. And remember, you can use that chat to, if a question comes up in your mind, you can put it in the chat, and that's a way to kind of hold it so you don't forget it. Also, I kept a couple of the questions from yesterday as well that we didn't get to. We'll address those as well at the end. So the topic of corrosion control is what we're going to talk about now. We'll start out with defining what corrosion actually is, and I have some kind of basic definitions here. In corrosion, we're in water systems, we're basically talking about metals, metal pipes, and appurtenances. And one way we can think about corrosion is that metals will deteriorate due to chemical or electrical chemical reactions. And the reason it occurs is because the metals are actually losing electrons in this process. It's kind of a complex process. It involves some concepts of physics and chemistry to really describe it. But from a layman's perspective, like myself, the material that's corroding loses electrons, and that changes the state of that material. So it's a solid material, and when it loses those electrons, it can actually go back into solution. In other words, it can dissolve back into solution. If it's iron material, it loses its electrons, it goes into solution, and can end up ultimately forming as rust somewhere else. That place where it's losing material will form pits, or it'll actually see material loss, and this can happen through various means. The metal can react with oxygen in the water, or there can be some kind of electrical current that's causing this flow of electrons to occur. And another way to think about it is metals just simply returning to their natural oxide state. When you mine for iron, you will find iron in the natural environment in the form of iron oxide. So I guess if we think about it from that perspective, it's not too surprising that metals that are isolated that we use for building, it's kind of an unnatural state. So some various problems that we're worried about from the perspective of the distribution system. One category is that we can have a lot of breakdowns that cause outages, and we can have higher repair and replacement cost. That 2 a.m. Main break that wouldn't normally have happened if we didn't have corrosion, it causes a lot of unnecessary cost and results in a lot of public health risks and also even safety risk as operators have to go out at night to an unplanned repair or maintenance event. It can also lead to tuberculation, which, as you see an example here on the screen of a pipe that has tuberculation, it's a reaction between iron corrosion processes and bacterial processes that are interacting with that iron, and it leads to these growths that can actually reduce the volume of the pipe. And as you can imagine, looking at this pipe here, it also can create a environment where bacteria can live and thrive, and it increases the friction of water trying to move through that pipe. A main thing that we're concerned with when we talk about corrosion control is lead and copper, especially lead being released into drinking water, and just deterioration of pipes and equipment. Um, and finally, leakage and water loss can be an issue. Let me move on to the next slide here. Now, the causes of corrosivity. We have various water quality factors that can lead to corrosion or cause corrosion. First of all, we can have low pH and alkalinity. A low pH is acidic, as we looked at yesterday, and a low alkalinity does not buffer the acid. Excuse me for a second. Also, the levels of dissolved inorganic carbon. We talked about yesterday dissolved organic carbon, but inorganic carbon can have an effect on the corrosivity of water. Carbon is a form of alkalinity. A high chloride to sulfate ratio. When you have salts, if you have a lot more chloride than sulfate, that can lead to corrosivity. And just high total dissolved solids in the form of salts, dissolved oxygen, and even carbon dioxide. If you have carbon dioxide in the water, for some reason, it can lead to a lower pH and corrosive water. So if you look at this image on the screen, it's kind of summarizing all the different forces that are working against the integrity of that pipe. You have things like water hammer, external pressures, internal pressures, leaks, but when we look at all the corrosion factors here in the yellow the yellow bubbles, the water quality issues, conductivity, the microbiological activities, and the type of water, those are all factors that can affect corrosivity of water. And we also have the possibility of having electrical or galvanic currents. If you have a galvanic situation, you'll have an anodic site that gives up electrons and a cathodic site that receives electrons. So for example, as the example I gave before, iron atoms lose electrons from an anodic site and they lose them to a cathodic site, and you'll end up having pitting on that anodic site. And you can see that process there, that iron coming out of that anodic site. You notice it has a +2 has a positive charge. That's because it has lost electrons. And you see on the bottom inside of that metal, that electron is traveling through the metal to the cathodic site, but the iron ions are actually moving through this solution in water. So it's quite an involved process. I'm not even sure if my explanation really accounts for all the complexity here, but I hope it gives us an idea. You have ions traveling through the water and electrons traveling through the metal pipe. And ultimately, you'll see with iron, you'll see iron oxides like rust formed and deposited. And you notice in this pipe, even though it's the same pipe, when we talk about cathodic reactions in a couple slides, we're going to see that we have two different types of metal, and one has a greater propensity to give up electrons. In this case, the same pipe has an anodic site and a cathodic site, and that can occur for a number of reasons. Let's look at the galvanic series here. I just mentioned different dissimilar metals, and the concept here is if we have two dissimilar metals that are connected, the more reactive metal is going to give up electrons and become the anode. And I in this galvanic series, I just chose some of the most common types of metals, but the galvanic series has, dozens and dozens of metals. So let's take a look here at this chart here. We have from the less reactive, platinum and gold, they're very unlikely to corrode, all the way down to the more reactive metals such as zinc and magnesium. They'll give up electrons very readily. And in general, the electron flow is going to go from these more reactive to the less reactive. The farther apart the metals are in the series, the greater the potential for electron flow. If they're close together, there won't be very much electron flow. And I'll give you a couple of examples here. Let's say we have an aluminum fitting attached to a copper pipe. Now, I'm going to circle those on the chart here. There's aluminum and there's copper. Those are fairly significantly far apart. What's going to happen there? The electrons are going to flow from the aluminum metal to the copper. Here's the next example here. A copper pipe is connected to a bronze fitting here. So you notice the copper is still involved, but what's going to happen between copper and bronze? The bronze is right above it. The copper was the cathode, but because of the arrangement of these two metals, the copper actually becomes the anode here between copper and bronze. So if there was any flow, it would be from the copper now to the bronze, but because these are such similar metals right next to each other, the flow between these metals might not be significant enough to actually cause corrosion. Now, water is involved as well. Now, pure water, H2O, is not really a causative factor of corrosion. Now, water does act as a medium for the transfer of electrons, and water can form an electrolyte solution based on what's dissolved in the water. So, for example, if we have a bunch of salts, we have sodium chloride dissolved in water, it makes a bunch of positive sodium ions and a bunch of negative chloride ions, and that creates an electrolyte solution that allows current and ions to flow through it. So it acts as a medium, and they say it's kind of like a catalyst, which facilitates other reactions to take place. The chemistry of water can increase corrosivity, and I've heard of a lot of explanations where they just say the chemistry of water can increase corrosivity, but what does that actually mean? Well, we're talking about things like, is there a high level of dissolved oxygen where there's oxidizers that are readily available? Do we have high salinity from dissolved salts? Does the water have a low pH and a low alkalinity? Those are things that would increase corrosivity. And of course, the opposite is true for every one of these as well. A low dissolved inorganic carbon content. All those things can increase corrosivity. If we look at our image at the bottom right, you notice that it says we have an electrolyte in the form of H2O, and it's carrying ions. It has the positive iron ions that are flowing through it. The electrons are flowing through the iron material from anodic sites to cathodic sites, and we have this. So we have some pitting going on where corrosion occurred and redepositing of some rust, and it could be tubercles. There's different types of corrosion, and there's more terms than just these, but the type that we were just looking at, where corrosion is occurring in a pipe and we have a transfer of ions and a transfer of electrons, that we'd call that an electrochemical reaction. Galvanic corrosion, we'd be talking about two dissimilar metals that are either physically connected, like a fitting connected to a pipe, or they're connected through some kind of electrolyte solution. We can also have kind of generalized corrosion. That's a form of corrosion that kind of equally affects an entire pipe. Like you see a pipe that it's all kind of rusting at the same rate. There's no focal point that's causing pitting or anything like that. That would be called generalized. But when it's focused at a point, they call that pitting corrosion. Crevice corrosion would be something like that image you see on the right hand. You see some kind of some generalized corrosion there, but you can see that there's also some corrosion that's focused on the mating parts of the flanges and so forth. The crevice will tend to collect water and possibly even particles that facilitate corrosion. And this image that just came up here is an example of a copper pipe connected to an iron pipe. And you see there's a couple different things going on there, but this would be a good example of galvanic corrosion. But what they also are indicating in this particular image is they're applying some cathodic protection. The natural flow of electrons is from anode to the cathode. So if you apply a small millivolt direct current in the opposite direction, you can actually disrupt that flow of electrons and stop that galvanic reaction from occurring. Differential corrosion is a different term, and an example of that on this bottom right image here, you have a tank and it has varying levels of water that expose kind of that fill level, that movable fill level to periods of oxygen and water, and that can result in some what they call differential corrosion. So there's lots of different terms to describe how corrosion manifests itself and the types of corrosion uh, by the causative factor. So here's what we just looked at. We were looking at when iron, especially cast iron. A lot of our systems have old cast iron pipe. And when you connect a copper pipe to it, well, what actually happens? It actually can lead to excessive corrosion of the cast iron because the cast iron is more reactive than the copper. And here's an image of a cast iron pipe that had a copper service. There's a little inset image in that image on the left, and this is uh, the same pipe. You can see that cast iron pipe it just corroded on the outside and probably the inside as well. It just really destroyed it because of the galvanic corrosion that was going on because of that copper pipe being connected. So the cathodic protection, like we were just saying, it actually works in the opposite. It sends direct current in the opposite direction that the natural corrosion processes want to go. Normally, it's from the anode to the cathode, but you can apply either something like a zinc um, sacrificial anode, where the electrons will come out of it rather than your iron pipe, or you can actually apply a little voltage there where it sends the voltage in the opposite direction. And here we have these two types of iron here, metals, I'm sorry. We have iron and a zinc, and we have some current flow because we have a water with dissolved, uh, in this case, dissolved hydrochloric acid. We have HCl electrolyte, which means we'd have positive hydrogens and negative chloride ions that allows electricity or current to flow. And so that all of these reactions are facilitated by having electrolyte in the form of water. Also, corrosion is involved with the destruction of things like lead pipes and copper pipes that cause us to have problems with the lead and copper rule. And there's different solutions for that. Most of the time, when you have a lead and copper problem, you can do something like adjust the pH and alkalinity of the water, which makes it less corrosive. Um, but you may also need to have a feed of orthophosphate. We'll talk about that in a second. And what that does, it helps to create kind of a coating. We talked about the problems of hard water where it can cause scaling. When we add orthophosphate, we're actually inducing scaling to have a very thin layer of scale on the inside of the pipe, a phosphate layer, and it kind of protects the pipe, and it also binds those lead um, ions that have been, or lead or copper that have been uh, corroded from pipe. It'll actually hold those and bond those in place. In this image here, they have something else going on. They were talking about not only creating those scales, but using some cathodic protection in addition to help to facilitate and maintain those scales. Here's an example of a sacrificial anode. On the upper left, you see a cross section of a steel pipe going through the ground, and it wants to corrode. The iron uh, wants to uh, wants to give up its electrons to whatever is going on either in the inside of that pipe or on the outside of the pipe. The outside of the pipe, it might be exposed to groundwater, and the electrons are trying to be ripped out of that steel pipe. But if you add a magnesium rod, for example, and connect it to that pipe, when there's a demand for electrons, the magnesium rod can very easily give up those electrons instead of the steel pipe. So the electron demand is satisfied without damaging the steel pipe. And the corrosion, as you can imagine, we're talking a lot about electrical flow between dissimilar metals, and this is the concept of the battery. And this particular image here represents one of the early studies or attempts to create a battery. It's kind of interesting. On the copper side, the electrolyte solution was a copper sulfate solution, and on the zinc side, it was a zinc sulfate solution. So there's something going on there where there was two different uh, types of electrolytes, but the concept here that you had a zinc and a copper. Notice if you look at that upper uh, wire that's connecting these two electrodes, you see the current flow, and that's going from the zinc to the copper, and that's because zinc is a lot more reactive than copper. And most of the time when you have a sacrificial anode, it'll be either zinc or magnesium, because those are the most reactive metals of the different options. When you want to measure the intensity of corrosion, you can use something known as a coupon. And here's some examples of some different types of coupons here. There's a aluminum, a steel, a brass, and a copper. But the idea is that the aluminum, I'm sorry, that the coupon will match the material that you're trying to protect. So if you have a cast iron pipe, you'd want a cast iron coupon. If you have a ductile iron pipe, you'd want a ductile iron coupon. And basically, these are placed in the flow of the water, and over a period of time, they're taken back out and weighed to see if they've lost any of the weight from corrosion. You can get an idea of the intensity of corrosion that's occurring. You can have a device called a coupon rack where you actually install these, where it allows the water to flow uh, past. And you see on the top of that coupon rack, they're taking out, they've unscrewed a cap and they're pulling something out there. That's what they're pulling out there is one of the coupons. So they can easily just pull those out and look. So this might represent different types of material that are in the distribution system. You can just pull them out, clean them, and weigh them and see if you've lost any material. They weigh them before, and then after 90 to 100 days, they take them out and they weigh them again. There's different ways to protect pipes and tanks, and you can have linings like you see here on the top right. There's some ductile iron pipe that's been lined on the inside with cement, and you can see that white layer of grout or cement where they actually have lined that. There are techniques, this is new pipe. There are techniques to do some grouting in place. So you can have a machine that goes through and grouts the existing pipes if you need to. You can also have coatings. Coating is something you would put on the inside of a iron storage tank. There's also wrapping. I didn't get any images of that, but you can actually wrap the external part of a distribution main, wrap it with a plastic material on the outside to prevent external corrosion. And of course, cathodic protection is the use of either sacrificial anodes or some kind of a DC current to reduce the electron flow, or both. Here's someone that's actually applying a coating to the inside of a storage tank. And there's different chemicals used, different materials used, I should say, epoxy resins, metallic and non-metallic paints, even glass-based type of coatings. And there's a bunch of proprietary coatings out there. They keep on improving in this area. But whatever is used, you want to make sure it meets the NSF 61 standard, which has to do with materials that come in contact with water. And this image here is from a tank inspection, a tank that did not have an interior coating. But every so often you have to recoat your tank. Let's say it's every 12 to 15 years, maybe in ideal situations. Could be faster in unideal situations. But there's different tests that they use. One test is just simply it's like a piece of tape that they put on the coating, and they pull the tape off and see if the coating comes off with it. But one of the things they're really looking for is there any pitting in that coating. And a thing to think about is if you have just even a small hole in the coating, all of the corrosion forces will be focused on that one hole, and it can cause pitting. So it's something that where every 3 to 5 years when you're having a tank inspection, that's one of the things they're going to inspect. And that's also something you want to account for in your asset management plan, is that, hey, we're going to be needing to recoat our tank every 10, 12, 15 years, something like that. And so that's an expense to budget in. And it is important for water quality. Here's an image of a a cathodic protection system for a storage tank, and you see that there's a DC current generator, and we're talking about microamps that's flowing out to the sacrificial anodes, and and it's causing a current to flow from the anodes to the tank. So in essence, instead of the tank being the anode and giving up electrons, the tank is really kind of the cathode, but you don't want a bunch of material to deposit onto the tank either. So In reality, you're keeping it almost neutral, but you're sending enough current so that the tank there's not electrons coming out of the tank. They're coming out of the sacrificial anodes instead. The Langelier index is a way to evaluate corrosivity. So the Langelier saturation index, LSI, and that will tell you if the water is likely to be corrosive, scale forming, or if it's stable, which means it won't be scale forming or corrosive. And so the pH of a water when it's at saturation means that when the water is just saturated with calcium carbonate, and that depends on temperature. So how much calcium carbonate can be dissolved into a water? Well, there's a limit. If you go over that limit, it's not going to dissolve anymore. It's going to precipitate out. But when it's just saturated with calcium carbonate, and that changes with temperature, but that's the saturation pH. So you add calcium carbonate, and then when it's saturated, you measure what's the pH of that water. So that's your saturation. Then you look at the actual pH of the water. And the equation is the actual pH minus the saturation pH. So if it's negative, that means you have a corrosive water. If it's positive, it means you have a scale forming water potentially. And if it's near zero, it indicates that it's not going to be corrosive or scale forming. And I'm going to give you an example here. We have a water and we measure the pH. The actual pH is 6.8, but its saturation pH is 7.3. Predict if it's going to be scale forming or corrosive, and here's how we would plug it in. We'd have a negative number because the actual number is 6.8. The saturation pH is 7.3. 6.8 minus 7.3 equals a negative 0.5. So that means it's corrosive water. So some things that we could do would be, for example, we could just increase the pH to 7.3, and then it's not going to be scale forming or corrosive. And we may also need to add alkalinity. We don't know that until we would actually see what the alkalinity is and if we have a corrosion problem. Another test that we can do, or a assessment we can do of the water, is to look at the chloride to sulfate mass ratio. And this is something that came out of the Flint lead crisis. The chloride in milligrams per liter is divided by the concentration of sulfate in milligrams per liter in a water. And obviously these are both, these can be both types of ions from different compounds, but they call it the CSMR. And if this results in a factor that's greater than 0.5, it can mean that the water is corrosive. So the milligrams per liter of chloride divided by the milligrams per liter of sulfate. And here's an example here. We have a source water and it has a chloride concentration of 10 milligrams per liter, and it has a sulfate concentration of 22 milligrams per liter. We'd obviously get this with water quality testing from a lab. And then we can use the chloride to sulfate mass ratio formula to predict whether the water is corrosive. And so here it is. We have our CSMR, 10 milligrams per liter of sulfate divided, 10 milligrams per liter of chloride divided by 22 milligrams per liter of sulfate. And that gives us a factor of 0.45. Let me know in the chat, is this water corrosive or non-corrosive? What do you say? I put you all to sleep out there. Okay, right. I see a lot of non-corrosive answers. Thank you. And of course, since the value 0.45 is below 0.5, the water is considered non-corrosive. Excellent job. Thank you, everyone. Now, if we need to add alkalinity or increase pH, this would be one of the easier things to do to reduce corrosion. Now, what is alkalinity? Is usually carbonate and bicarbonate chemicals that we can add. For example, calcium carbonate is a form of alkalinity. In general, if alkalinity is below about 30 milligrams per liter, that's pretty soft water, and it's more likely to be corrosive. If you start getting above that, it's a lot more workable. And for corrosion control, if it's above 150 to 200 uh, milligrams per liter, that's ideal for corrosion control. It might not be ideal for everything else, but just for the narrow scope of corrosion control, getting up into that region between 150 and 200 is considered ideal for the corrosion control. The kinds of chemicals that we add to increase alkalinity can be something like hydrated lime, and that has a good impact on alkalinity without really affecting the pH too much. Where soda ash also will increase alkalinity and pH. So if you had a low pH and low alkalinity, soda ash might be the thing to add. And something like sodium hydroxide or lye, that pretty much just increases the pH without really doing much for the alkalinity. So different options. It's kind of like having different golf clubs out on the golf course. What are your goals? Are you trying to increase just alkalinity or both? And we have a poll here. Water has a chloride concentration of 15 milligrams per liter and a sulfide concentration of 21 milligrams per liter. Is the water corrosive? And of course, we would use all of these type of measurements, pH and alkalinity, the CSMR, the Langelier index. We would use, and looking at the water quality overall, the total dissolved solids, and so forth to help us to make the best decision for corrosion control if we have a problem. For example, most of the time we would know that we have a problem if we have lead and copper results that are over the limit, or if we have a lot of problems with leaks and main breaks, and then that would probably prompt us to investigate more. But we use a variety of techniques. And I see most of you, 87% or so, are saying yes, this water is corrosive. And let's look at the solution here. Our CSMR is 15 milligrams per liter of chloride divided by 21 milligrams per liter of sulfide, and that gives us a CSMR of 0.71. It's greater than 0.5, so you are correct that this water is likely to be corrosive. Great job, everyone. I want to talk a little bit about a couple of lead contamination events here, and kind of the lessons we learned from them. We had Washington, D.C. In 2000 had a significant lead in water problem. It was actually worse than what happened in Flint, which we'll talk about there. But in the DC water systems, what happened is they switched. They were trying to meet the disinfection byproduct rule, and they switched from chlorine to chloramines in the distribution system. Seemingly a pretty innocuous change, but it disrupted the pipe scales and led to a release of lead into the drinking water. In Flint, Michigan, they actually switched to a different water source, the Flint River. There was already a treatment plant in place there, a large treatment plant already set up. It turned out that water source was corrosive, and one of the factors that was used to analyze the corrosivity was the chloride to sulfate mass ratio. And both of these events actually ended up changing the way we approach the lead and copper rule. It's very much the same as in Milwaukee when there was that massive cryptosporidium outbreak, which, with 400,000 people got sick from cryptosporidium, and it changed the surface water rule because we learned lessons from those. And you can read more about this at this link. You'll have this slide on your handout, and it was the Flint water crisis, what happened and why. You can read about Flint. Now let's look at the DC first. So they switched from chlorine to chloramines to comply with the disinfection byproducts rule. Now, before that, this happened in the year 2000, and it kind of was an ongoing thing between 2000 and 2004, I believe. And they're still battling with it. The image on the screen is a 2023 image where the red sections are places are within the DC water system that still have lead service lines. So it's an ongoing challenge. So, but prior to that, they had been using chlorine for a long time, and they had this long period of time during which they accumulated a scale in the inside of the pipes that had lead inside the scale. It was retained, it was safe, it wasn't going anywhere, and it was a lot to do with chlorine. The chlorine there that was being used, fairly high chlorine levels, helped to form these scales on the insides of the service pipes. When they switched to chloramines, it changed the oxidation reduction potential at the pipe surfaces, and this previously stable lead scale was now dissolved and was released. So they had decades of this built up mineral coating in the service lines, and then it was dissolved and lead was allowed to leach into the water supply. Uh, the peak measured levels for compliance sampling, and Daryl will talk about this a little bit later, but you're looking at the 90th percentile. However, in individual homes, there was some independent tests done where lead was as high as 308 UG per liter. In other words, parts per billion. The action level for lead is 15 parts per billion. And so that even that at 80, that's several times over the action level. And about 100,000 people were exposed to lead above the action level. So this was a real learning curve about switching from chlorine to chloramines. And by 2004, they switched to an orthophosphate feed, and they've had it under control since then, and they're still battling to remove the lead surface lines. Now, Flint, there's a little story here. They switched from this Detroit water source, which was kind of like they purchased treated water, to the Flint River, where they already had a treatment plant constructed, and that was mostly because of economics. The Flint River was a kind of unstable and corrosive. It had kind of higher organics, so they were also having problems with disinfection byproducts. It was kind of variable quality. But part of the treatment treatment choice involved using ferric chloride as a coagulant, and they had a reason for doing that. They were trying to meet also disinfection byproduct rules and so forth, so they chose ferric chloride. Now remember, in the previous slide we looked at the chloride to sulfate mass ratio. So the water was already corrosive, and then this additional ferric chloride added more chloride to the top of that CSMR when you look at it from that perspective. So that added to the corrosivity. Now before that, there was 45 years of this Detroit water flowing through the pipes. and Detroit water had a phosphate feed. So inside these pipes, there's a 45-year buildup of scale inside the Flint water pipes where the lead was captured in the scale. And so the corrosivity of the new water coming in caused this lead scale containing lead to be released. Eventually, they did return to using the Detroit water, but it took a while to correct the situation. It took a while to rebuild that scale, so they used a little bit of combination of orthophosphate feed, a little bit of additional feed uh, to build scale, and also some system flushing to flush out the disrupted lead contaminants in the form of sediments. And today they're in compliance. They're doing great, but there's some factors that we should consider. The CSMR, the chloride to sulfate mass ratio, was actually at least 2.04, which is obviously that's above 0.5, right? So this formula might have been used in some places before then, but since the Flint uh, crisis, this is a more widely used formula. Another problem is that as corrosivity went through the system, iron pipes, especially cast iron pipes, also were corroding, and that ended up consuming chlorine. So you had two things going on. Not only did you have the release of lead scales, but you also had the threat of reduced microbial control as chlorine was consumed. Massive chlorine demand from the iron pipes. Also, Flint operators didn't really have a complete picture at first because they had sample sites that didn't prioritize what we now know as tier one sites, which Daryl will explain later. But we we now focus on sites, choosing sample sites that we know will have something like a lead service line or a galvanized service line, but they didn't really have that. So there was, based on the samples that were collected, they didn't really have a full picture of how bad the problem was at first. But there was some independent researchers that came in from I think it was Virginia Tech, and they did some independent sampling, and also they found that there was elevated blood levels, especially of children. That's what kind of brought the issue to the forefront to be looked at more closely. And really, the highest 90th percentile readings that they found was 57 parts per billion. And they found that in 2019, as they were well on the way of correcting this situation. But remember, in DC, it was actually as high as 80, and there was results uh, as high as in the hundreds at individual homes in Flint. And remember, in DC, there was a reading at an individual home of over 300. So actually, the DC event was actually a bigger, a worse crisis. Now you can look at. There's a study, an excellent study here in the NIH, and the link is at the bottom here, and it's called Evaluating Water Lead Levels During the Flint Water Crisis. So it goes through it very factually, not a politically agitated uh, article, but a scientific article that goes through all these things. The diagram at the bottom, you can see what was going on with the corrosive water, and where it says Flint River water, they had the release of the lead scale, the lead containing scale, and then they started feeding the orthophosphate, and they started reforming those scales. And at the same time, they were using flushing to get rid of the lead containing sediment. So it was quite a process. A lot of work went into this to restore the system. And so I guess the moral of the story is you have to be really careful when you change water source or the disinfection type. You want to pilot those two things first. How phosphate works, it actually creates a protective layer of scale on the inside to protect against corrosion, and also binds lead and corrosion byproducts. It can be fed as phosphoric acid, uh, zinc orthophosphate, or a potassium-based salt. If you use phosphoric acid, that's probably that's kind of easy to feed, but it also requires special handling, as phosphoric acid would not be something you'd want to get in your eye, for example. And the dosage is normally between about 0.5 to 1.5, so right around the range that you'd feed chlorine, actually. You want to keep it below 10 part per million because you don't want to have excessive scale buildup. That can cause just as many problems as it solves. And if you're feeding orthophosphate, that's been shown to be effective even in transitions from chlorine to chloramine. So that would be something that you'd want to consider if you need to change to chloramines in the distribution system. Also, it seems to work best between pH of about 7.3 and 7.8. All of these major changes in things like pH and disinfection type and so forth, these also can affect other compliance objectives. For example, having a high pH might be great for orthophosphate. It's not going to be quite as good for disinfection efficiency. Biofilms can actually also affect corrosion. If you can imagine that biofilms are right on the surface of the pipe. So instead of it being pipe and water flowing right against the surface of that pipe, instead now you have bacteria against the pipe wall. So water is no longer in direct contact. So what is in direct contact? Well, the biofilm could be producing different pH levels against that pipe wall. The oxygen levels could be different near that pipe wall. The bacteria could actually be facilitating the corrosion depending on the type of pipe. And so biofilm actually it interacts with different types of pipes in different ways. And it can even create a low pH at the pipe surface that ends up leading to corrosion. And it can also help to form tubercles. What you're seeing here on the image here is different stages in biofilm growth. And you see the bacteria attaching and beginning to grow in the first slide. In the middle slide, you see the biofilm is fully forming within 6 to 10 weeks. And then after that, bacteria can actually break off of that biofilm and go to begin growing in other parts of the distribution system, but it can also begin to help the corrosion process to do things like pitting and forming tubercles. Tuberculation is a potential outcome of corrosion when you have iron pipes, especially something like cast iron pipe. And so what's really happening here is iron bacteria are involved, and their iron bacteria are helping to oxidize that iron and form a precipitate. And when you see the tubercles growing, um, that's a combination of bacterial action and the corrosive action and forming a basically rust. And once you get tubercles growing, it acts as kind of a substrate that facilitates more bacterial growth. And as you can imagine, a pipe that has tuberculation like this is going to be significantly affecting the amount of horsepower it takes to push water and the flow that can go through that pipe. So you're going to have reduced flow, more horsepower, and the pipe is in bad shape. It's more likely to break or have leaks. The things that affect that would be things like water age, uh, high, a low pH and alkalinity, high temperatures, high water age, levels of uh, total dissolved solids, and if you have microorganisms that are actively growing in biofilms, and the problems that we just mentioned, reduced pipe capacity, increased friction, reduce water quality, and breaks and leaks. Those are all the problems that will result. Lead service lines here, there's an image here that shows One of the potential locations where there could be a lead service line pipe, gooseneck or a pigtail, they might call it. In this case, we're seeing one that's coming right off of the water main. And of course, further down that line to the house, there could be other, depending on the age of the house and when plumbing was installed, there could be uh, other lead containing components there. So when we connect or see a connection between a lead pipe and let's say that goes to a copper pipe, the lead is actually the anode in that situation and can corrode. This image that you're seeing here is the inside of a pipe. It's been cut lengthwise through the middle, and we're looking at the scales that are in the in that pipe. Excuse me. We see some at Pb carbonate. That means a lead carbonate scale, and Cu sulfate. That's a copper sulfate scale. And so all these scales are in this pipe, and under very low conditions, uh, they they might just stay right there and not actually make it into the drinking water supply. But if there's something that disrupts these, like say somebody goes in and they say, "Hey, I'm gonna help you out. I'm gonna change out. I'm gonna remove your lead service line," and the plumbing gets disrupted, that could be something that causes the lead scale to move. Different flows, um, anything that disturbs that or different water quality can cause all of a sudden a large amount of lead to be released. And here's an example of a couple different plumbing arrangements here. You have lead with copper. The lead is the anode and it's corroding. And you have lead and brass that contains zinc and copper. And in this case, you have a couple different reactions going on. The zinc corrodes preferentially to the lead. The lead corrodes preferentially to the copper. There's a number of decision trees that you can find on the EPA manual. I've included it in your references and I'll show it here as well. But as you're trying to figure out what is the best decision to make for corrosion control, first of all, you'd look at pH and alkalinity, the water chemistry, uh, decide whether you need to feed a corrosion control inhibitor like orthophosphate, because if the pH and alkalinity won't do it, if adjusting the water chemistry won't do it, then you probably have your last resort is either to feed a corrosion inhibitor or to replace the materials. But you can see a lot more if you download this manual, Optimal Corrosion Control Treatment Evaluation. It's technical recommendations manual. So you can download that. I highly recommend it, and you can walk through step by step. Inside a pipe, biofilm can actually interact with scale. So you have corrosion products actually interacting um, between scales and biofilm processes. And I'm going to show you an example here. There was a study done, and they had these 30 feet long sections of pipe, different types of pipe. They had PEX, copper, galvanized steel, and PVC. And each of them had a 2-foot section of lead pipe at the beginning. And so they flowed water through the pipe for 7 months to simulate regular residential use. And after 7 months, the lead pipe was removed and flow was resumed for a couple more months. So they had this lead pipe, and that's simulating going into their plumbing at the beginning. So that would be like having a lead service line that goes to your plumbing. So what did they find? They had a gradual, after the beginning, they had a gradual increase in lead content in the biofilm of these pipes. And they had as high as 48 parts per billion in the biofilm. And after they removed the lead section, they had a sharp increase in the biofilm lead concentration. And it increased about 13 parts per billion in the biofilm. And so what that tells us was when they removed the lead service line, that actually caused these scale particles to be dislodged and to move downstream in the biofilm, and it became a potential secondary source of lead contamination. So if you can imagine that biofilm, it has a life cycle process where it will have where it will dislodge and move farther down and reestablish itself. If so, you're totally at the mercy then of what this biofilm is doing uh, as far as moving the lead contamination around now. So that's another risk. All right, we're going to do a second poll here. In the DC water crisis of 2000, why was lead released when changing to chloramines? All right, we got about 75% participation here. I'm going to move forward here and oops. My little thing went out of place here. Sometimes those little circles move around. So in this case, when they changed to chloramines, they had an existing pipe scale, remember, that it contained lead, that changed the oxidation reduction potential, and that was dissolved and released lead into the water in the DC crisis. The chloride to sulfate mass ratio was more what happened in plant. Now we're going to go through cross-connection control kind of briefly, and then we're going to be handing it over to Daryl. Now, cross-connections. A cross-connection is just a link or a channel that can potentially connect water with a source of pollution. And another way to think about it, it's a plumbing pathway that contamination can travel through, so that contamination can enter a water distribution system when there's a reversal flow. So backflow is actually a reversal of flow normally from a customer's plumbing, a source of pollution, or an unapproved source into the drinking water supply. And it's a problem because it can lead to illness. Uh, there's two elements that are required for a backflow. You have to have a cross connection and some kind of pressure differential for it to occur. And the example of an example of uh, one form is back siphonage, where you have a loss of system pressure, and that could be caused from a fire flow or a main break or some kind of outage, but it makes it possible for the non-potable substance to enter. Or you can have a back pressure where the customer pressure exceeds the system pressure. Might have chemical feed pumps or some kind of boiler, a process that overwhelms the pressure of the system. And let's see, let me move this out of the way here. You can also have other means where contaminants can enter through some kind of sanitary deficiency, like an air release valve, where backflow could occur. Here's an example of some different forms of backflow. We have a main break that causes the water pressure in the line to be reduced. And that creates a reversal of flow. And here we have someone connected to the system. There's a hose, a submerged outlet into some kind of a chemical storage, and it's going to be able to flow through that pipe back in through the faucet and into the distribution system if those are all connected and if there's low pressure, which causes a vacuum. So if we don't have any backflow protection, some dangerous contaminants can be drawn in. Here's an example of a submerged outlet. that can cause back siphonage, and what could protect that from happening is either to avoid, of course, having a submerged outlet, and not allowing your hose to be submerged in a some kind of a contamination tank, but also just having a backflow device such as a vacuum breaker on a faucet can protect that. So an inlet pipe that feeds into the bottom of a tank can be something that's a submerged outlet. So imagine you have a full tank of chlorine. Even I've seen it happen in even water systems where you have a chlorine basin, and instead of pulling from the top, it is pushing in from the bottom. It's going so that could just sit there and siphon and allow too much chlorine to go into the system. A basin that's being um, filled where the hose is submerged below the liquid surface, and something like an air release valve or screened air vent that's below the flood line. Those are all examples of a submerged outlet. A direct plumbing connection, sometimes you need to, for example, send to an industrial process a good pipe, a good source of pressure and flow through a pipe where it's providing sufficient volume and pressure. Uh, that would be an example of a direct connection. And if there's some kind of low pressure in the distribution system or high pressure on the customer side, backflow can occur. So you might have some kind of a pipeline that puts you in direct contact with some kind of commercial process or industrial chemical process that doesn't have adequate backflow protection, and you can end up with contamination in your water distribution system. And another example, a service connection with the customer's plumbing is connected to a private well or some kind of other high pressure source of liquids that or gases even without adequate backflow protection. There's been situations where people people were taking a shower and all of a sudden they started getting chemical burns, and their skin was actually being destroyed in the shower because there was a situation where there was a chemical uh, sodium hydroxide. Either they were manufacturing it or they were using it, and there was a backflow of that sodium hydroxide and caused chemical burns unexpectedly all at once. The people weren't ready for it. They were in the shower, they had these chemical burns, and imagine if you drank that, you would have chemical burns all the way down. There's been situations where people had their toilet blow up. There was a situation where there was gas, natural gas in the pipeline, and so there was a story where a guy threw a cigarette in a toilet, and the whole bathroom blew up. There's been all kinds of situations like that. There was a situation where people went to drink from a drinking water fountain, and it was blood red with contamination from a slaughterhouse floor, where they had some kind of pump that was removing it. So there's some pretty gross things. And if you look at backflow events, some of the things that have happened have been amazing. Here's an example of a situation where you could have back pressure. You have water being supplied from the water main on the left, and it goes through to the customer side. There's a booster pump and a chemical feed that allows gravity flow, and that can, if there was a backflow where you had a loss of pressure in the main, it can allow that chemical feed to re-enter the not only the customer's plumbing, but actually eventually make it to the water main. And here's again a little bit closer up of our submerged outlet at a home. This could be somebody just filling chemicals to treat their lawn, and they don't have a vacuum breaker. There's a low pressure in the distribution system. Those chemicals can be drawn in. And here's an example of what might cause a back siphonage event. Here's a car hitting a wet barrel hydrant, and there's a massive loss of pressure, and there's some kind of a submerged outlet at point A in that home, and it causes a backflow that person that's drinking water on the first story is affected by it, and everyone downstream can potentially be affected by it. Fire flows can be something that can create a low pressure. a main or hydrant break, and even sometimes elevation differences. The type of device that you use, the level of backflow protection, depends on the degree of hazard. For the highest hazards, you might completely disconnect. So instead of having a direct connection, you have you have an air gap. There's a physical disconnection that completely separates the system. That's for the highest health hazards. A reduced pressure zone device would be for moderate health hazards. Double check low health hazards, and vacuum breaker would be something that you would use at the water users level, like a residential water, and that can be for a variety of reasons. And here's a diagram that shows you application of those different hazard levels. At the bottom, you have a boiler, and that's a potential to create a backflow from back pressure, and they have a reduced pressure zone backflow preventer there. At a shop sink, they have a vacuum breaker. At a cooking cafeteria, they have a double check valve. Photo lab, where you could have chemicals, they have a reduced zone. And for a dishwasher, they have a atmospheric vacuum breaker. So different levels and the different levels relate to the health threat. Here's an example of an atmospheric vacuum breaker. As water flows through this, it basically pushes that seal out of the way, that disc seal out of the way. As soon as water is turned off, that will drop back down and block the flow. So if there's an attempt for water to reverse flow, it wouldn't be able to do it because that seal would drop. Into the path of the water. Here's an example of a pressure vacuum breaker, and it's pretty much similar, the same thing, except it has an additional spring here that makes it a little bit more positive. It's not just falling back down under gravity. It has a spring that has to be overcome when the water's turned on, and when the water's turned off, the spring holds that valve in place to prevent backflow. A double check valve is basically just two check valves in a row. It just give you redundancy. Those check valves they're spring loaded also. They're pushed out of the way and open when water is flowing. As soon as water stops, the spring closes them. So it's just two redundant valves in series. In in a reduced pressure zone device, it's basically like a double check valve, except there's an added um, component where the water that's in the valve, if it closes, will be vented to the atmosphere. So it actually opens the circuit if there's a backflow, and it kind of has the advantage of like an air gap, because you don't have continuous plumbing anymore. And this is for higher hazard areas. And an air gap is the highest level of protection. And air gap, you want to have the distance between the air the supply pipe and the tank that you're supplying water to should at least be twice the diameter of the pipe. And here's an application of an air gap. You have a situation where you're supplying water at a sewer facility where you would definitely not want to have any backflow occurring, and that little circle there above that water that should be a distance of twice the diameter. Some aspects of a cross-connection connection control program, the goal is to prevent harmful substances from entering the drinking water through backflow. And so you're also identifying uh, and eliminating any cross connections and sanitary deficiencies in the system, and applying some uniform codes for everyone to follow. And there's different elements that you would need the legal authority to enforce. You'd want to have a comprehensive inventory of every type of contaminant source and potential cross connection. You want to make sure there's some kind of a way to train people. In a lot of cases, small towns may have, they may require the owner of the potential cross connection to hire someone to come out and test their backflow devices, and they would need to submit records of that test each year. And so you want your backflow devices to be inspected at least annually and maintained, and a full report, because when you have a sanitary survey, that's one of the things that you want to be able to show them. We have a cross connection control program, and here's all our records. And our final poll here before we hand it off to Daryl, poll 3. Which device would allow the minimum necessary protection from back siphonage when filling a chemical tank at a residence? What would you use? And Daryl, I'm gonna stop sharing and let you come in.
Okay, Greg, thank you. So let's see, we've got responses, just over half are in. Let's see, we have 51% saying vacuum breaker, 29% air gap, 10% double check, and 10% reduced pressure zone assembly. Let's see. And the answer is C, vacuum breaker. Right. So at this point, I think we're probably time to take a break. How about we take a 10-minute break, Lori?
That sounds good.
All
Okay.
right.
We'll see everybody back on the other side. I hope you all have a good break.
Thanks. Okay, looks like it's time to get started back. So we'll be talking first about sanitary surveys. So these surveys are typically conducted by the primacy agency, whether that's your state or another entity. One thing I want to point out is that a lot of people get concerned about the primacy agency coming out and doing this sanitary survey, and you really you shouldn't be concerned. I think that as someone who's done sanitary surveys from the regulatory standpoint and received them, it's most of the issues they come up long before the sanitary survey comes about. So why do they do them? It's a chance to identify any potential risks to public health. They ensure that the water system has the capacity to deliver the water that they need to their constituents. And it's an opportunity for the primacy agency to educate and provide technical assistance. Keyword there, we pull out capacity, so that's important. So the reason for them, they're required under both the interim enhanced surface water treatment rule and the groundwater rule. The frequencies that are established are typically every 3 years for community water supplies and every 5 years for the non-communities. We're talking about capacity. So TMF capacity, technical is performance of assets and ability to operate and be maintained, managerial processes for maintenance and replacement, planning and coordination, financial, sufficient revenue. So you need the money to make sure that you can maintain and replace assets. So these things all come together, and they're the three parts make up the TMF capacity for a system. And we've, if you've ever had an asset management course, you've talked or you've heard all sorts of information about TMF. So what is capacity from a utility standpoint for both management and operations? All right, so there's several different things. Sufficient, this slide it is directed towards a wastewater system. In that case, you'd have sufficient collections, pumping, and treatment capacity. And for a water system, you would have sufficient treatment, pumping, distribution, and storage. You want to be able to have that, all the time, 24 hours a day, 7 days a week, and 365 days in a year. You have the need for redundancy and backups of the critical infrastructure, the stuff that you really need. You're going to want to have that ability that if something goes down, you can continue to operate. Your workforce needs to be properly trained. They need to be able to perform the tasks that they need to do to make sure that things are operating correctly. Your policies and your standards, your procedures, making sure that everybody's doing the right thing and in the same way, that's important. And once again, we had mentioned the money. You need to have the money to cover your operation and maintenance and any debt service that you might have. It's important as part of that to have a capital improvement plan so that identifies what you're going to spend your money on in the next over the next 10 years or so. So what are the elements of a typical sanitary survey? So we cover the water source, where we're getting our water from, how we're treating our water, the distribution system that the water goes out into, and any finished water storage. It also involves the pumping and controls, both from, could be from the source, it could be out into the distribution system. They look at the monitoring and reporting, what testing you're doing and how well you're doing about reporting those results to the primacy agency. Looks at the management and operations of your system and operator compliance. So do you have the right level of certification for your operators, and do you have enough of those operators to operate your system? So as we see, each one of these is kind of identified throughout the system. So prior to the survey, I would recommend that people go through their records and make sure that they have the stuff that the primacy agency is going to be looking for. You want to have it available, and you can expect that they're going to want to go through and tour the water system. So after the survey, what do you expect? You're going to get a letter that should detail any of the findings that they've come up with, especially in any deficiencies. Hopefully there aren't any, but they'll come up with those, and they'll give you a timeline for you to correct those deficiencies. What are the different categories for the deficiencies? So, the most important one is if you happen to have a significant deficiency. So that's something that could cause health risks. You could be contaminating, there could be contamination in the water. Those are the highest of importance. We go on down to moderate. Those are issues that might not be an immediate threat, but if you let them go, there could be something that comes out of that. And then minor ones are less serious. It's something that is going to, in the long run, be better for you to change your process potentially, but at this point, it's not serious. So let's look first at the water source. So during a sanitary survey, you'll come out and they're going to look and make sure that you have a safe and reliable water source. Look at well construction. are there any sources of contamination that could affect the well? And look at how you're transmitting your water. Some of those common deficiencies, your well is not constructed properly. If you look at the figure on the left, the cap is broken and there's a chunk missing from it. If you look at the center one, that's too close to the ground, so it's subject potentially to flooding. Typical requirements for casings above ground are around 18 inches, but it's, each state has its own well construction standards, so it's specific to your locale. And then, do we have a well that's located too close to a surface water body, potential flooding from that? Is it too close to known sources of contamination as well? We look at the treatment, some of the things that would potentially be looked at in a sanitary survey are how effective the treatment processes are. We'll include disinfection and filtration in that if you've got a system that does those. Common deficiencies listed: a lack of monitoring points for chemical additions. So, you're putting the water or you're putting the chemicals in, but do you have the right places to sample and test to make sure that you're doing it right, that you're receiving the right concentrations? Are you storing your chemicals properly in a safe manner, in a manner that will keep them from somehow getting into your potable water? Let's see, cross connection between the chemicals or the waste flows and the water. Once again, we're looking out for cross connections. Do you have any issues with MCL and residuals? And is the water being properly treated and monitored? So in this situation, you got potential for backflow due to the lack of an air gap. Those pipes were plumbed directly into a drain, which could be full of water, and then you lose pressure, and it gets back siphoned in. So as we said, all the chemicals, they'll look at what chemicals you're using and make sure that they are NSF approved and that they're properly stored. The distribution system becomes a little harder to do an inspection on. Most things are below ground. So they'll look at the condition of, what's the condition, the age of your water system, how well are you doing maintenance on fire hydrants, what's your flushing, are you turning valves, things like that. How up to date is your cross connection program? Are you getting out and doing inspections? Are you having other inspection reports brought in and making sure that these things are getting looked at? It could get into, is the system properly sized? Do you have issues with the wrong materials? Have you had low pressure, or do you have excessive leakage in the system? In this case, obviously you've got a broken fire hydrant, so there's something that's not going to be of any use to your system. The figure on the right, distribution of air valves. So they're in a pit. You need to make sure that there's a screen vent so that stuff's not brought in through the vent and potentially cause contamination. Finished water storage. It seems to me that this is one of the more common areas that things get called out in a sanitary survey, and probably because it's very visual. You can see quite often, especially if it's an elevated storage tank, it's up in the air. Everybody knows where those are located. So you'll look for safety and security issues, potentials for contamination. And one of the things that these screens are quite often brought up as the 24 mesh screens are something that is commonly called out. We got some unprotected openings in the top of the tank, a damaged screen on an overflow pipe. And as I said, the 24 mesh screen is one that is often brought up in sanitary survey reviews. So it's funny. I would often hear, well, we've had that screen on there for years and it was never a problem. But it's something that as these sanitary surveys are being developed in the primacy agencies, that it gets called out in EPA's training manuals. So pumps, you're going to assess the functionality and the maintenance. Does your pump work? Are you keeping it up? Are you having it inspected and tested to make sure that those things operate properly? So this figure shows an example of a redundant pumping system. You've got two pumps there, so that I'm assuming that they're there in case if one goes down, we've got a second. We can make sure that we continue to provide safe water at proper pressures. The figure on the right shows a flooded pump meter pit, and that's not good because the damage that can happen to any of the meters in there, the potential for any sort of a equipment being damaged, or somehow get some water from the pit into the system. Common deficiencies: you don't have enough capacity in your pumping. You don't have redundancy, so you don't have enough. You don't have something in case something breaks down. You can't ensure that you're going to continue to serve the public. If you have pumps that cycle too frequently, some of the problems that can happen with that is you can burn a pump out. A lot of pumps are cooled by the water that goes through them, and if they cycle too often and for too short of a time, they don't get the opportunity to cool off. Issues with screens, that can be a problem. Have you had a history of either outages where you're not able to serve the public, or you have low pressures? The next topic we have is operator compliance. So are your operators qualified? Do they have the proper licensing, and are they getting the right training so that they can operate and maintain your water system? So do they, as we said, proper operator certification? So it goes into both the type and level for systems. Quite often those are based off of the size of the system, whether it's what their capacity is or the population. Do you have enough operators? If you're a system that has to provide 24 hours operations, do you have enough people to operate your system throughout the 24 hours a day? And then you have to document your training for your operators. A lot of times that stuff is it's covered by the primacy agency when they give out their operator certifications and when they do renewals. Management and operations. So we're going to look at how is the system is it operated as a whole? Do we, once again, we get down to the money. Are we doing financial planning? Are we planning for the future? Funding our system, proper rates? Are we doing are we maintaining the records according to what the primacy agency requires? And then are we planning for any contingencies or emergencies that might be out there? Some of those things that we would look at from an operations and management standpoint are the policies and ordinances that are in place. As Greg talked about, do you have a cross connection ordinance in place? Financial management, are you doing asset management? Are you, do you have a capital improvement plan? What's your system area, service area? So are you aware of where all your customers are? I had mentioned asset management, emergency response planning again. Are you doing any public notification that's required? You know, if you've got issues that come up, are you properly notifying the public? And then, you know, the consumer confidence report, is that being, is it put out in a timely manner? Is it, are all your customers receiving it according to your requirements? Are you maintaining your cross-connection control records and submitting those to the primacy agency? And then, you know, any record of previous sanitary surveys, or that's another thing that you need to keep on file. Documentation of ownership. If you know, if you're not a municipality, you're owned by another entity. And then permitting. You need to get permits and you need to maintain permits according to your primacy agency's requirements. So quite often, you know, systems will have emergency response plans, but they don't seem to want to keep them updated. So that's something that quite often is found as a result of sanitary survey is it's not that they don't have one, it may be that they can't find it, or that it's not up to date. You know, quite often people change, those names don't change in it. Companies that you may utilize in emergency situations change and they don't get updated. And as we had mentioned, you know, the financial side, are your rates adequate? Do you have enough money set aside in order to do any necessary repairs or any system upgrades? So now we're going to go on and look at our monitoring and reporting. This includes what are your system's practices for monitoring? What do you collect? Whether it's sample results from required testing or not. What are your sampling plans? You know, your bacterial, your site sampling plans for bacteria, your disinfection byproducts plans. What kind of measurements are you taking out in the field? It could be a chlorine residual, could be a phosphate residual if you had phosphates, and any reporting procedures that you need to do in order to make sure that you're meeting your requirements and you're in compliance with regulations. As I said, site sampling plans for coliform, DBPRs. Let's not forget the lead copper rule. Any water quality factors, things you need, treatment process control. So what you need, there may be things that you collect and it's not necessarily required to report, but it's part of the process. You need to have a certain level of something in order to make something else work. And then those that are actually required for compliance. Disinfection residual monitoring, the fact that you're using approved laboratories for any testing that you send out, especially stuff that's that requires, it's a compliance-based testing. In your laboratory, do you have a process for calibrating your instruments to make sure that the results that you're getting are actually valid results? And then what kind of sampling procedures do you follow? All right. Next, we have a poll. All right, Lori's brought that poll up. Which of the following do you think is a tier 1 sanitary deficiency? A water operator has not attended a training in the last 10 months. B, the end of a tank overflow pipe is 20 inches from the concrete pad. C, a well casing does not have a sanitary seal. Or D, the system is understaffed. Okay. Let's see. We're getting some responses here. We're just over half of the participants have responded at this point. Give it maybe another minute or so. Let's see. We're about 2/3 people or so. All right, let's go. And at 84%, our leading response is C, a well casing does not have a sanitary seal. So, and the answer is C, a well casing does not have a sanitary seal. And that's so an uncased well, an unsealed well casing, it could allow contaminants to enter the water. So that's considered a potential public health situation, and that meets the criteria of a type tier 1 sanitary deficiency. All right. So now we will move on to sampling and monitoring. All right. So why do we, other than somebody telling us that we have to monitor our chlorine residuals, why do we do it? Well, one of the things is because they tell we have to maintain a maximum residual disinfection level below 4 parts per million. And that's important because, that level indicates that, could potentially cause harm to the people drinking the water. The other reason is that we need to maintain minimum residuals. It's 0.2 parts per million for chlorine and 0.5 part for chloramine. And it also helps us to ensure that, we're protecting against those pathogens, the reasons that that's one of the main reasons we're putting in chlorine, and to inhibit that biofilm from growing on our pipes. If you had too low a residual, there's more, as we talked yesterday, there's more potential for that growth of the biofilm. And those numbers, they can give you an indication a little bit earlier than you might otherwise find that maybe there's a contamination occurring, but we just don't see it. Maybe we didn't get a bad bacteriological result, but there's something out there that's using up our chlorine. So it's good to know that ahead of time. And he said, you want to make sure that you get at least 0.2 parts per million, especially out in those areas that maybe don't get as much. You've got older water, they don't get as much use. You have dead ends. So what do we, how do we measure for it? One of the most common one is the DPD method. It's, as you can see, we'll just call it DPD rather than try and pronounce that long chemical name. So DPD is used, it's a reagent that's used, and it changes color in the presence of chlorine. So if you look at those vials at the bottom of the screen, you can see that what we go from a low chlorine residual on the left to a higher chlorine residuals as we go across. So we see a color change when we put that into water. Typically, we test for free residual for chlorine, but we also can test for total residual for chlorine. But for chloramines, we test predominantly for the total residual. And this just shows a DPD pack being opened into a vial of water to do the testing. This shows what a vial may look like, and with a chlorine in it, showing the pink. This is a handheld device that so we would take our vial with our DPD in the water, and we put it into the handheld device, and it would give us a reading that would tell us. This is an example here of the old chlorine dials, and that's a it's an actual dial that has the colors on it, and then you do a comparison of that the color to come up with a number. One of the problems with these things is that the dials tend to fade through time, especially if they're exposed to sunlight. And one of the an operator's favorite place to put these things is on the dash of their truck, their work truck. So so quite often we would that becomes an issue as those fade. So most people are going to more of the digital meter for those. And this slide shows the effects of time on chlorine residuals and temperature as well. I think I said yesterday that chlorine is most effective at higher temperatures, but it also has it lasts much less. So as the slide says, chlorine decay is largely a function of time, temperature, and demand. So those are the things that can, if it weren't for those, you'd probably have consistent chlorine residual throughout your system all the time. So if we look at this spot, we have a chlorine residual of 0.2 after 7 hours. And then it drops off as time goes on considerably in this study in Chile. You can reduce the chlorine demand by, if you can get those sediments out of your pipes, you need to get it up to scouring velocities. If you clean storage tanks, it's surprising how much stuff can settle out in the bottom of a storage tank through time. Replacing or lining cast iron pipes are notorious for having tuberculosis or tuberculars on them, and that can affect that chlorine demand. And it's said water age. If you gently flush those dead ends, you can make sure that the water's fresh and it's going to have the higher chlorine residual in it. And this is a study in Korea where they looked at how chlorine residuals decrease as you get out into the system. The darker area to the left is where is closer to the treatment facility, or where the chlorine, where the water is fresh and new. And as it goes out, you can see that we've got bands, but in general,
It's right up there. You can see it.
oh, yeah. All right.
Or we can use the
Yes.
later pointer.
So it comes in here. We've got a residual, of 0.01 and a residual of 0.5, 0.05. Even though the residual is coming in around 1, dead ends in the remote parts had residuals below 0.2. So that's one, as we mentioned, we want to stay above 0.2. Booster disinfection. So they were, the study considered whether do we need to put booster disinfection locations out there. And as we talked with disinfection byproducts, that's all stuff we have to consider when we're going through this. Is it worth adding additional chlorine and potential to form disinfection byproducts out in the system, or are we better off doing flushing? But like I said, in some cases you may need to boost the chlorination out in the system. So the total coliform rule. A couple of the most important things that we're going to look at are going to be the repeat sampling requirements and the number of samples that are required. There's a mention of the quick reference guide below. As I had said before, those are very important documents put out by EPA, and it'll show up on the screen here eventually, but I encourage people to make copies of those, print them off, have them digitally, whatever the case may be, because they're great sources of information if you need something in a hurry. required repeat samples. All right. So if you've got a routine sample that tests positive from your distribution system, you have to take repeats in the following 3 locations. So you have to repeat the original site. So the place that came back positive needs to be tested, but you also have to go within 5 service connections upstream and within 5 service connections downstream. So those 3 samples. If you're a small system, a system that has a population of 1,000 or less, that means that you would be taking 1 sample per month normally. So in order, if you do have that routine sample comes back positive, you have to go to a 4th location in the distribution system. So you'll do your upstream, your downstream, your original, and another one. As we said, the number of samples based on population. So the next screen will show us the populations. If you're in a system that serves 4,900 or more people, you can collect, or 4,900 or less, you can collect samples on the same day. But if you're a larger system, you need to spread those out at regular intervals throughout the month. So you can't collect all your samples in one day, you need to spread them out. There's that quick reference guide that I'd mentioned. I would encourage you when you get the PDF of this that you go and look at that. And this chart here comes from that quick reference guide. It shows based off of population how many samples are required to have per month. And as we said, if you get to this point where you're at 6 samples per month, you need to spread those out throughout. So the larger you are, the more samples that you're going to have to collect routinely throughout the month. So EPA, in addition to the total coliform, came out with a revised total coliform rule. It added E. coli as an MCL, and it came up with a find and fix approach. So if you have an issue, you're going to go out and you're going to identify any sanitary deficiency you have that may have led to the total coliform or E. coli positives and address those. So a level 1 assessment requires the utility to investigate any sanitary deficiencies. So this is the lowest level, and it puts it on the utility to go out there. And that happens if you've had 2 or more total coliform positives in a month, and systems, and that's for systems that have routinely collect 40 or fewer samples. If you were at a larger system that collects 40 or more, it's based off of 5%. So once you get to 5% of your samples came back total coliform positive, then you have to do a level 1 assessment. So a level 2 assessment, that moves up in severity. It's performed by the state, and it happens when a utility's had 2 level 1 assessments within a 12-month period, or if a system has an E. coli violation. So as this process goes on, I would expect that even if it's a level 1 assessment, you're having communications with your primacy agency, and they can let you, they can make sure that you're on the right path and you're doing the things you need to do. Obviously, when you get to a level 2 assessment, they're going to be involved for sure, but it's always great to have good communication with your primacy agency. All right, so some of the concepts to keep in mind. If there's going to be a contamination issue, you're going to have a source for the contamination. You're going to have a way for the contamination into the system, and you're going to have a mechanism that causes the contamination to enter the system. Here's the revised total coliform quick reference guide. It's the bottom of here. Once again, I can't say enough about those documents and how important they are to have. So next we'll look at our sample siting plan for coliform sampling. So it's important that everybody submits a report to the primacy or a plan to the primacy agency, and quite often they'll do a review on it and report back to you whether it's approved or not. The samples are supposed to be collected at points in the system that are representative of the distribution system. In that plan, you have to identify those repeat sample locations. So you're going to have to identify a sample location within 5 connections, both upstream and downstream. So there'll be 2 samples there. And the idea, what's representative? You know, we need to have different types of population served. Are there different pressure zones? Because if there's different pressure zones, you're probably going to have different potentially different water in each one of those. They probably won't mix. Or, you know, do you have different geographic areas, things that are separated by geography, or do they have different sources? Do you have a well that provides water to this area of town and a different one that provides water to that area of town? So this shows that there's an example of a single site. So routine samples at 1, 2, 3 Groot Drive. The repeat obviously is the same. And then you have your upstream and your downstream are either 189 or 100. So to further illustrate that, so here we have 123 Groot Drive. That's our routine sample site. And we've selected 100 and 189 as our upstream and downstream sites. So we're saying that downstream is to the right of our sample site, and that makes upstream to the left. So if we look at this, we go from here, we've got 1, 2, 3, 4, the 5th service connection. Okay, so we're within 5. And if we go downstream, we've got 1, 2, 3, 4, and our 5th. So this site right here would not be eligible to be a downstream site because it's beyond 5 service connections. So now we're going to look now a little bit more at the sampling side. So what we have here is a coliform sample bottle. It's used, you know, for collecting coliform samples. So that sample bottle has in it a dechlorinating agent, and the idea is that you know, we want to make sure that if we're adding chlorine to this, that sample doesn't the chlorine doesn't continue to work in that bottle after we've collected it. So when you collect these samples, I'll try and do a little visual. There's a little plastic, clear plastic that goes over. You peel that off. You unscrew the bottle. You make sure that you keep the cap, the top up and the bottom down. You don't want to turn it because then something could fall into that cap. And you collect your sample, and then you put the cap back on. So as much you want to do as little handling of anything. You don't never want to touch the rim of the bottle or of the cap or anything like that, because you can contaminate those potentially. The other thing is you want to fill that bottle, and you want to try and fill it right to that 100 ml line every time. It's, you know, you don't want to be short water, you don't want to have extra water. So this shows the sodium thiosulfate tablet. That's what's used to dechlorinate the sample. Some important tips when you're collecting samples. So if you've got a sample site that has a threaded on, maybe it's got a hose that can connect to it, those can be problematic because they can harbor bacteria. So you want to avoid those. You also want to ensure that your tap's well above grade, so that there's nothing, it doesn't get flooded, and there wouldn't be any reason to have bacteria potentially in that water that gets on your tap. You want to run the water for a significant amount of time, you know, and at least until you can notice that there's a temperature change, because you want fresh water. You don't want water that's just been sitting in the home or business's plumbing. And then if you have the ability, you want to disinfect this. First, you can use alcohol. I mean, that's almost always alcohol. We've told people to use chlorine or bleach on it. Ideally, if it's a faucet that allows it, you torch it. And so one of the best sample taps is you have a stainless steel gasketless valve, and that's important because that's less likely to a gasket, rubber or something like that could harbor bacteria. Also, if you want to flame it, it could cause problems and melt, that gasket. But if you've got a small diameter copper tubing, gooseneck, something that you can flame, those are great sample taps. We'll look at the lead and copper rule. So this establishes the action levels for lead and copper. For those people in Michigan, you'll note that Michigan went and they changed theirs. So it's not 15 parts per billion, but it's 12 parts per billion as of the first of this year. So the rule is based off the 90th percentile. An easy example is if a system collects 10 samples, you put them from the lowest result to the highest result. If there's 10 of them, you disregard the top result and take the 9th one. So that's your 90th percentile. There's ways that you can do that that identify for other numbers, but that's a simple. It's by 90th percentile, they'd mean like the 9th out of if there were 10 samples in from lowest to highest. It's a first draw sample. That means that you're collecting the water that comes right out of the tap. You don't run water and then put your sample bottle under there. You collect it right from the beginning. And EPA wants that tap to have not been used for the previous 6 hours. Standard sampling is every 6 months. That can be increased or decreased based off of your results that you're getting, your history. And an action level exceeding is not a violation, but it's a trigger for other things. So do you have to do water quality parameter monitoring? Is there a corrosion control treatment study required? Do you have potentially an issue with either your source water or your treatment? You may have to do public education to let them know about the results. Or if you've got lead service lines, you're probably going to have to do some lead service line replacement. So there's the quick reference guide for the lead and copper rule. And that for the lead and copper rule revisions. So let's look at the sampling and the different tiers. So this identifies, this slide shows based off the size of a system, what their standard and potentially reduced number of lead and copper samples are required from the distribution system, and any the water quality parameter tap samples that you might have to collect. So if you're trying to develop your sampling plan for lead and copper, you're going to look first at your single family homes that have copper with lead solder constructed between 1983 and 1988. And any lead pipes, including lead goosenecks or pigtails, or full-blown lead service lines. Those are going to be your first ones. So you need to populate it, your sampling plan with those first. If you don't have enough, then you can move on to tier 2, which is all building types with lead and copper solder within those constructed within those same dates, and the lead goosenecks or pigtails and lead service lines. So if you go through and you've taken all your tier 1 and you've taken your tier 2 and you still have to collect the additional samples, then you would look at single families, homes that have copper with lead solder constructed before 1983. So the idea is that lead and lead solder should have been out of the plumbing materials in 1988. EPA, when they created the rule, said that at that time, those 5 years from 83 to 88, that's what they were keying in on, and it's not really changed since. So that's why those dates are what they are. And then if you've exhausted all those the tier 1, tier 2, and 3, then you're allowed to go on to other, and they just need to be representative of the plumbing and homes in your system. Disinfection byproduct rules. DBPRs, it's based on your locational running annual average. So we talked about this stuff yesterday. Trihalomethanes and haloacetic acids form when chlorine reacts with organic compounds in the water. So those people that add ozone, they have to do testing for bromate. That forms when there's bromide in the water and you use ozone for a disinfectant. Testing for chlorides are required when you're using chlorine dioxide as a disinfectant. And then here's the quick reference guide for the DBPR rule. Disinfection byproduct compliance and sampling. So the MCL for total trihalomethanes or TTHMs is 0.080 milligrams per liter or parts per million, and for HA5 it's 0.060. Once again, I said that compliance is based off the locational running annual average. So each site that you collect from has to meet those, and it's a quarterly sampling, and they compare the average of the previous 4 sets of samples to these numbers here. And when you're deciding on your sample locations, you're required to do an initial distribution system evaluation. With that, you're gonna look at your system and you're gonna try and figure out what areas are pretty much what's the potential for the worst. Where do we have older water, less water use, and so that all plays into where you set up these sites. So it ends up being kind of a worst case situation. So something about the bottles that are used for HA5 samples, use a glass bottle. It's got a preservative in there called ammonium chloride. Obviously, you have to be concerned with your safety. You don't want to get that in your eyes, on your hands, or anything like that. With that bottle, you fill it to within 2 inches of the top. We can call it the shoulder or neck of the bottle. And you want to place it in a cooler with ice. The sampling for TTHM is interesting. And with that sampling, it's very important that there's no air in the bottle. So that's one. I would recommend to people who have never done sampling for total trihalomethanes or volatiles, because they use the same type of bottle, that you practice with it. And maybe you get an extra set and you just run through it, but it's important because it needs to have all the air out, and about the only way to do that is almost have a water bubble, not an air bubble, that goes over the top of the cap. And then you carefully put that cap on to make sure that no air gets into it, because that can invalidate that sample. And then these samples are really important for temperature. So it's important that they're on ice and that they get to the laboratory quickly, so that they don't. For a time frame, we saw a lot of samples that were invalidated because they didn't meet the temperature requirements when they were received or processed at the lab. So definitely something to keep in mind. The number and frequency is based off of the size of the system. Subpar H are going to be your surface water systems. So if we look at just the groundwater, we've got a population between 500 and 10,000, and we're on an annual collection. We have to do once per treatment plant, or it could be per, in this case, quite often it's per well if they're in different areas. Stage 2, got to do 2 distribution system monitoring locations per year. The next part of our sampling is the chain of custody. So this is a document that ensures that it helps you, the laboratory, know what samples come in and what they need to be tested for. But it's a legal document that makes sure that the process is being done correctly. So in our chain of custody, we're going to have a sample identification, includes an ID, date, time, and location of the collection. We're going to have information about the sample's source, what preservatives are used, what analysis we're going to have done on it. It includes the transfer, so that it documents the date and time. It has signatures for individuals relinquishing and receiving custody. So if I take the sample and I give the sample to Greg, I sign off on it, he signs off on it, we make sure that that it's documented that I gave him the sample. So now it's in his hands. It's important to, that we have the proper storage of preservative. And like I said, sometimes it comes down to temperature. The lab, when they ultimately receive the sample, they're going to verify that the chain of custody is correct. It's got all the information that it needs to have, and that it doesn't appear as if anybody had tampered with the samples. And then, that chain of custody is maintained as part of the official record. And that's usually at the laboratory that they maintain those. Here's an example of a chain of custody. We've got information about the company. We've got the sampler, including their signature, information about the sample, date, time, things of that nature. What analysis are we requesting? What do we want to have done? How many containers are included? The temperature. So those are all important things. So at some point you will likely fill out those forms. Tiers of public notification. Tier 1's an immediate notice. That's something that's, potential human health issue. Those are very important. They have a very regimented notification methods, and they are immediate. So you would be in contact with your primacy agency if something like that is required. Tier 2 is, it's not quite as important. It doesn't pose a immediate risk to human health. And those are within 30 days, and they've got some less restrictive ways that you can get that information out. And the least restrictive is the annual notice of a tier 1. It didn't violate a drinking water standard, didn't have an impact on human health. Sometimes these are failure to collect a sample, failure to report something. And one of the mechanisms for delivery of that is the annual water quality reports. If it lines up time-wise, you can put it in there and you don't have to have a separate posting. The elements, description of the violation, including the contaminated of concern and the level, when it happened, why it happened, what are the potential health effects. Important thing is there is language that they want to see with that. What's the population at risk? Is anybody vulnerable to this? Do customers need to seek an alternate water supply? Do they have to get bottled water or something like that? What's the system doing to correct the problem? What can consumers do to help themselves out? Should they run their water for a certain amount of time? Should they boil their water? Stuff like that. When do you expect to have the problem resolved? Give contact information, name, phone number, email addresses for the people that the customers can go to find information. And then, they want you to make, what are you doing to make sure that this is getting to everybody else? So it may just be a note saying, please share this with others outside of the community if you know that they use the water. As we said, tier 1 it's very important. It needs to be issued as soon as practical, but not less than 24 hours of learning. These are typically fecal or E. coli violations, nitrate or nitrite, maximum contaminant level violations. System that adds chlorine dioxide it went over they went over the maximum residual disinfection level. A turbidity level exceedance for a filtration plant. If there's a waterborne disease outbreak or emergency, something that we had talked about before was Legionella, detection of E. coli or other bacteria, certain bacteria in a groundwater source sample, and then other violations or systems as determined by your primacy agency. So they can bump those up. Here's the public notification quick reference guide, consumer confidence report, different elements, violations column. They've got the contaminant column. We've got them organized by different types. Sometimes states will add, in this case, they have a lower fluoride level requirement than the federal level. What are the MCLs? What levels are we trying to meet? There's a table key that tells us information about those. They're required to be distributed for the prior year by July 1st. So those that were for 2024 were due by July 1st of 2025. You need to work with your primacy if there's any required language and how to get those out. There's a quick reference side. And one of the things I wanted to point out is that CCR certifications that say that we did this work are required to the primacy agency by either October 1st or within 90 days of when you send it out to your customers. So that's another thing that needs to be added. Okay, so we're on to poll number 5. Lori's got that up. The poll is what would be wrong with collecting a coliform sample without having a dechlorinating agent in the sample bottle? A, the chlorine could damage the plastic bottle material. B, nothing, just write this on the chain of custody. C, the sample would not be representative. Or D, it would result in a false positive test. Okay, getting some results in. Okay, well, we've got, let's see, just over 2/3 of the results in, and the predominant answer is C, the sample would not be representative. We've got that at 73%. The 24% is D. Let's see what we got here. So the sample would not be representative, and that's because there's the potential that the chlorine that's still in that bottle could kill some of the bacteria. And so that would not be, that sample could actually give us a false negative because the chlorine would be allowed to continue to act on the water in there. And by the way, a total coliform negative is actually a good thing. So, so what did we cover today? We covered corrosion control. Greg did that. Greg talked about cross-connection control. And I just finished covering sanitary surveys and sampling and monitoring. Greg and I would like to thank you for your participation, as well as Lori, and I'm sure Lori and Ingrid as well. As Greg likes to say, please share one thing that you enjoyed learning about today in the chat, and we will open it up for questions and answers. Hopefully we have answers for you.
I got a couple questions for you. These go back to Greg's section though. So
Okay.
Greg, if you got your ears on. So the first question was from Tracy asking, we have seen submittals for DIP with asphaltic coating on the inside and outside. Is coating on the inside of pipe recommended?
Yes, that's a standard That's a standard method for protecting ductile iron pipe from corrosion.
Okay, ready for the next one? Okay, if this is from Nick, if replacing existing multi-material potable water plumbing in a home, what is the best material to lessen corrosion potential?
You know that if I was giving just a quick answer, I would say some kind of plastic material. But if your water is not corrosive, there is no problem actually with materials like copper. Um, so uh, you can't go wrong with plastic PVC or PEX or PE pipe. But copper is not a problem if there's no corrosion.
Okay, thank you, Greg, for that. Um, that's all I have for questions right now, unless they keep coming in the chat. I did put the SurveyMonkey link into the chat for those of you that need a certificate of attendance. Please make sure to send that in within the next 24 hours. It does expire. So if you didn't see it in the chat, I'm gonna drop it in there again.
And I brought up our slide with our information. So if you have a question that you would like to direct to Greg or myself directly, we've got our email addresses up there.
Hey, Daryl, how much do they have to pay us if they want to request technical assistance?
Well, I think that number is 0. I don't think that we charge for technical assistance.
I was thinking about something when you were talking about chlorine residual as an early warning sign. I remember one system that I was helping, and they said, we have this funny thing happening to our residual. And they had this one, the transmission main came from the well and it went out through the community. And when we tested the water on one side of a street that it crossed, it was like 1.0, something like that, milligram per liter. I can't remember the exact. And on the other side of the street, it was 0.5, something in that nature. It was like half. The chlorine was half, just like suddenly along the same transmission main. And so we started investigating it, and it turned out that there was some kind of an agricultural well that was installed, and for some reason they ended up hooking it into the distribution system. So there was actually, it was an unapproved source with no chlorination going on. It it turned out there was nothing really wrong with that water, so nobody was getting sick. But we wouldn't have known that they had inadvertently hooked it to the distribution system, except for that chlorine measurement.
Yeah. Yeah. So I mean, there's the potential that it was using the chlorine up, but there's also more likely that it was diluting the chlorine by adding that water into the system.
Yeah, if there was some kind of backflow of contaminated water, but also uh, Walkerton, Canada. I'm not sure how many people are familiar with Walkerton, Canada, but they had heavy rains near their well 5, and there was a field within. I think they said 80 meters. So I mean, say that's 240 feet or something like that. So they had heavy rains and it washed in uh, coliform from a field that was fertilized with cow manure, and it percolated down into the well, and it used up all the chlorine, and it ended up 7, maybe 8 people died from that in a small town of just 2,000. But the big warning sign was the chlorine was used up, but the operators really weren't trained and they didn't recognize it at first. They just said, "Oh, chlorine's used up. Let me turn on some more chlorine," and they were a little slow at responding, and that went on for longer than it needed to, and there was some serious illnesses.
Yeah, very unfortunate event, but at least, hopefully we learn from that.
Yeah. I wrote down a couple of questions that we kind of missed yesterday. Someone said yesterday, are there any recommended filtration systems or other solutions for customers. Um, and I can't remember now what that was associated with. Uh, but at point of use, if you had at your home, uh, I would I would say the standard way to protect yourself from uh, contamination would be to have a reverse osmosis filter just for drinking. That a small unit like that would protect you from things like contamination and bacteria releases from main repair or whatever it is. And we also had something from a continuation of that uranium discussion. And I don't have the name here, but it says the EPA is telling us our water quality is not good, but how can we help it when we have had uranium mining from the early 60s in our area? The constant use of water used to stop the spread of plume mounds. We wonder if it is affecting our aquifer. So it sounds like maybe they have kind of a contaminant, possibly a contaminant plume, and there was some kind of a water pumping that was maybe pulling that plume back in one direction. But I was thinking some monitoring wells between their current source and the area of contamination might help them to determine if there is actually a plume going on. But it could also be a part of the source water, right? I mean, uranium is in the ground. It's a natural occurring contaminant from the ground, and I'm not sure if we have anything in additional to that except for possibly installation of some monitoring wells. And would something like a monitoring well, Daryl, do you know of any situations where that could be a funded infrastructure project to actually install something to investigate a source, maybe get a preliminary engineering report on that?
Yeah, I don't know. I mean, what comes to mind to me is from the contamination side, is there funding available to address, is there a situation where there's a potentially responsible party that caused it, or um, the so a state agency that covers groundwater contamination, do they have a mechanism to assist with that? The other thing, you could have, sometimes if there's contamination plumes, they'll install wells to intercept they pump the water out and potentially treat it, so to to not allow it to get to the aquifer, to the wells that serve a community. Um, it's an expensive endeavor though, because now you're pumping water that you're not actually utilizing for your customers, but you're, in essence, taking it out so that it doesn't contaminate the system.
But maybe we should add too, if somebody doesn't know about the process, the process to get funding begins with a preliminary engineering report called a PER, and that's an engineering investigation that you would have as part of a funding application. Like, for example, USDA gives infrastructure funds to small water and wastewater programs, and there's also a state revolving fund in each state. There are some applications that you can put in with EPA has a a technical assistance request form where they could potentially help you fund that PER. And the USDA has a search grant where you could apply to also get a PER done. And in both of those cases, you would have uh, kind of like a no cost PER that you could then turn around and use to apply for infrastructure funds. So that might also be the first step. You could contact Daryl or myself if you are in a situation where you need help applying on either of those. Does that sound right, Daryl?
Yes. Yes. It looks as if there's an issue with SurveyMonkey. I don't know if Lori, what?
Uh-oh.
Yep. It looks like it worked for some, and then it sort of crashed midway through. So thank you everybody for letting us know. We know you're here, right? We're gonna validate your attendance, but you have to send us an email at ctt@mtu.edu so that we know who had trouble and who didn't. Sorry about that, everybody. But I'll just put a reminder for that in the chat of what to do.
Thank you, Lori.
Mm.
All right. Well, we've been talking for a while and I haven't seen any questions come in, so. Suppose we can. All right, well, I guess Greg and I will probably sign off here and oh, we have a response from Wendell. Thanks for answering my question. They often tell us the levels are okay and not alarming, but we have had community members pass from cancer throughout the years. They use a high amount of water in springs and streams and have show to go down. Oh, we're moving. In levels or dry out to just a trickle of water. Okay. Well, that's sorry to hear that one.
And Wendell, you can contact Daryl or myself directly, and we could help you with some of those applications that we were talking about to get possibly a study done. Did you want to share the email again in the chat, Lori, just to make sure, or are you going to send it through email that to remind everybody of the issue?
I can put it back in there. No problem.
I missed it, but the chat's kind of moving, so
Yeah.
if you see what's happening, Lori is sharing again the email to, and the idea with the email, Lori, is for people to let you know that they had trouble.
Right, so we can record it in writing. So we have it documented how much trouble we had because the chat is flying really fast, right? And so it lets us attend to each person's record individually.
Okay.
So we don't miss anyone.
All right. I think we're going to sign off here.
That sounds good. I think I am going to just hang out for a little while since we had so much trouble in case anybody needs the message again. But thank you, everybody, for your participation. Thank you for the help in the background, Ingrid, and you guys for such a great presentation and good discussion. It's been fun.
Thank you, Lori, Greg, Ingrid.
Thank you, everyone. Have a great rest of your day.
Yes, you will get confirmation that your emails were received. They go to our general mailbox, but there's a real person monitoring it so that you do get a quick response. So I can actually see them coming in. So I can see that yours came in, Lapriel.